Hello and welcome to lesson 25. Today we're looking at one-sided limits. And your goal today, you can identify the need for a one-sided limit and you can apply those skills that I'm going to look at or teach you today to analyze an equation or a graph. So last day we talked about continuous functions and we said that if it has a value, if the limit has a value, then it's a continuous function. You don't have to lift your pen. We also found that not all functions are continuous, which means that we need to have a process to further analyze this discontinuous function. So one-sided limits are an evaluation process to look at f of x for some value a as we approach it from both sides. So what we're going to do is we're going to look at, and I got to fix the notation a little bit here, if the limit of f of x for a approaching from the negative side. So that means that, for example, if the a value is a 2, we're going to approach 2 from the left side. So we're going to be looking at 1, 1.5, 1.6, approaching 2 that direction. And then we go out the other way. So as we approach 2, we approach it from 3, 2.5, 2.2, 2.1 down to 2. If they're not equal to each other. So if we evaluate the limit coming in from both directions and they're not equal to each other, then the limit does not exist. The limit does not exist. So the function is discontinuous. So I got a bit of a typo here. So it is discontinuous. For the second one then, if the limit coming in from the left side, so again, it's the same thing, we're approaching 2 from the left side, so 1.5, 1.6, so we're sneaking up on 2, and then we sneak up on it from the other way, coming in from 3. If we find that it's equal to each other, it's the same value, then the limit does exist. So our limit does exist. So some terminology here. So the limit of f of x as x, the limit of x as we approach a from the positive side of f of x. So the limit is analyzed as we approach the x value from the left side. Okay, left side, which would be the negative side. All right. And then the limit for the other one is analyzed as we approach the x value from the right side, or the positive side. All right. And, of course, the symbols should be backwards here since I'm doing it. So this should be negative, and this one should be to the positive. All right. So, moving along here. Determine the limit for the following. So you've seen this in the grade 11 course, and that was the absolute value. So if you give yourself a bit of a sketch here. So what does absolute value look like? It's your V shape. So there is my function f of x. We want to do a one-sided limit as x approaches 0. So the limit as x approaches 0 from the negative side, the absolute value of x is equal to the limit as x approaches 0 from the positive side, the absolute value of x. So the first one I'm going to talk about here is this right here. Okay, what is the limit as x approaches 0 from the negative side? So what I am doing here, I am looking at approaching x of 0 from this direction. Okay, I'm heading towards 0, and I'm going to ask myself, what's the y value at that point as I approach from the left side? And the answer is it looks like it's going to be 0. Now, when I do the second limit, so as x approaches from the positive side of 0, I'm now putting my pencil on this side of the graph, and I'm heading back toward x equals 0, and I'm looking at what does it appear it's going to be. It appears it's going to be a 0. So therefore, the limit as x approaches 0 from the negative side, absolute value of x, is equal to the limit as x approaches 0 from the positive side, the absolute value of x. So that would tell me my final answer, the limit as x approaches 0 for the absolute value of x is 0. Okay? So our function would be continuous. Okay. So, there you go. Now it's a trivial example, okay, but I wanted to start with something that you're comfortable with before we get to more challenging work here. So what happens when, or determine if the following are continuous functions. So continuous functions means that the left side has to equal right side, or the limits, two-sided limits have to be equal. So, giving myself a quick sketch here, what does this graph look like? Absolute value, and it's been shifted left 2 units. So now it's over here. Okay. And I'm analyzing it as x approaches -2. So the limit as x approaches -2 from the negative side, and then I want to do an analysis as x approaches -2 from the positive side. Oops. So when I do this analysis, when I come in from the left, it looks like it's going to have a value of 0. When I come in from the positive side, it looks like it's going to have a value of 0. Because both sides are in fact equal, it will be a continuous function. So therefore, the limit as x approaches -2 from the negative side is equal to the limit as x approaches -2 from the negative side. So therefore, it would be continuous. Okay, the next function. I want to rewrite it because it's easier if it's one expression. So I need to get a common denominator. Common denominator will be x. So I end up with x squared minus 1. So, to give myself a sketch, I'll do it down here. I know that there's an asymptote at 0. Okay, and x squared minus 1. You guys can figure out that from that x squared, when x is positive, it'll be positive. So it's going to look something like this. Something like this. So this is from MHF4U, your advanced functions. You should be able to give yourself a quick sketch with this. All right. So the limit, and we're going to analyze it at where we think there's going to be an issue here, and that's going to be at x. So as we approach x from the negative side of 0, for x squared minus 1 over x, we're going to approach it then from the other side, 0 from the positive side. Okay. So as we approach 0 from the negative side, it looks like I am heading downward to a value of negative infinity. Okay. Okay. I just realized when I'm looking at this, there is x-intercepts, so these functions must cross the x-axis at some point. So they must go down and come up like that. It must be what it does here. Something like that. Because there are x-intercepts at plus or minus 1. Doesn't really change our original answer. It's still going to negative infinity. in that direction, I believe. No, my mistake here. It goes the other direction. I'm going to have to start fresh here. I missed my x-intercepts when I was thinking about the sketch. So the asymptote is at 0. So it must go like this and go like this. All right, so it does change my answer a little bit because now as I approach, it looks like it's heading to positive infinity. So what happens when you have a bad sketch? Got to be careful with that. When you're going to approach 0 on the positive side, looks like it's heading to negative infinity. So therefore, it's going to be discontinuous. That's because your left side not equal to the right side in terms of the limits. It's discontinuous. So we knew it was going to be discontinuous when we were looking at the asymptotes. Okay, for the next function, 2x over the absolute value of x. I'm going to look at the limit as x approaches 0 from the negative side for 2x over the absolute value of x, and the limit as x approaches 0 from the positive side. And the reason, again, I'm picking 0 to analyze is because that's where the issue is. Okay? If x is 0, that's where the problem arises. So what we can do is we can pick a number close to 0. Because the x-intercept, it should be going through 0, 0, but what we can do is we can pick a number close to 0 on the negative side. Okay, so let's pick negative 0.1. So if we use negative 0.1 just to analyze something that's really, really, really close, okay, what do we find? We know that the bottom will be a positive value always, and on top it's going to be a negative value. So it's going to head off to negative infinity. So I'm just doing a bit of a numerical analysis. On the other side, if we use positive 0.1, so again, just a little bit of a numerical analysis here for the limit, we find that the bottom is going to be positive, the top's positive, so it's going to head to positive infinity. So again, your left side and right side do not equal, so it is discontinuous at the asymptote. All right, and I'll finish up the rest of the examples in the next video.